Welcome to our series on the unresolved questions of evolutionary theory for ILBO Live. Today we talk about mass extinctions, what they are, how do they originate, and how do they work. And for this we have two special guests, both paleontologists. Michael Benton, who is professor of vertebrate paleontology at the School of Earth Sciences at the University of Bristol, and Massimo Bernardi, who is curator for paleontology and head of the research and collections area at MUSE, the Science Museum of Trento in Italy. Welcome and good morning to you both.
Good morning, thank you.
Nice to meet you.
So let's begin with you, Professor Benton. And I begin with a simple question. So what is a mass extinction? And how does it differ, in what terms does it differ from the background extinction rate? And because we're talking of unresolved questions, what is still today our level of ignorance about mass extinctions? Thank you.
Good, that's a lot of questions, but very important. So it's important that we understand that species go extinct all the time. We can't prevent all species from going extinct. But normally we would expect in the whole of the Earth, there are maybe 10 million species, and maybe only one species or anything up to 10 species would generally go extinct each year. And this is because a species doesn't last forever. We are Homo sapiens, we have been on the Earth for a few 100,000 years, but probably won't be here forever. We might evolve into some other species or disappear. And so if a species lasts for about 1 million years, there will be extinction happening. This is what we call background extinction, which is the normal level of extinction, which is like maybe 10 species a year across all plants and animals. A mass extinction is when lots of extinctions happen at the same time. It's at the other end of the extreme. And at certain points in the history of the Earth, as many as 50%, sometimes even 90% of species have gone extinct at the same time. So that is so different from the normal situation that we call it a mass extinction. There are all kinds of intermediate level extinctions as well. So for example, when sailors from Europe arrived on certain islands in the Pacific, they would kill species, they would eat them, that there would be a kind of local extinction of rare birds or something like that. Or at the end of the Ice Age, 11,000 years ago, lots of species of big mammals like mammoth and woolly rhino disappeared. But these were not mass extinctions because they were only in a particular part of the world or only affected particular kinds of species. And we've recognized maybe 5 big mass extinctions in the past. And then commonly we talk about the present day crisis, which we will talk more about, I'm sure. It's sometimes called the 6th extinction. Of course, as paleontologists, we could argue maybe there's more than 5 mass extinctions, and we may talk about that as well, which would mean we're in the 7th or the 8th, or who knows. But the key point is, arguably, there is good evidence that the current crisis is at that level, which then really, really makes this question important. It's not that, so my final point will be, we're not looking at the extinction of the dinosaurs. Oh, meteorite hitting the Earth, dinosaurs, bull. You know, which you could say that's kids' stuff, you know, it happened, but who cares? You know, what is the lesson for us? But the point we would make is there are many lessons for us by looking at mass extinctions in the past.
Let's continue with Professor Bernardi. And I ask you, what is the evolutionary significance of a mass extinction event? Should we say that there are regularities, laws during a mass extinction, or such events are totally led by chance?
Well, this is a huge debate. Even Charles Darwin was very much interested in the role of extinctions, even more than some of other younger, let's say, so closer to us paleontologists that work on extinction. Maybe Mike will elaborate on this, but in Darwin times, we didn't know much about mass extinction, but Darwin understood that extinction had something very important to do with the evolution of life. maybe and other very huge, incredibly important paleontologists. I was thinking, for example, at George Gaylor Simpson, for example, which is one of the fathers of our discipline, was not that actually clear, or actually was not that convinced that mass extinction really had a dramatic importance, no, in the evolution of life. So it's a huge debate that goes till today, but now we can say for sure that mass extinction are major boosters, major perturbations that do not only clear ecosystemic spaces, did not only cut, obviously, biodiversity, as we would expect from the term itself, but they've also there is also this other side of the process of extinction, which is really a way in which the macroevolutionary dynamics of our history, of our life, they are phases in which you are not able before the event to predict what would happen after the event, and this pushes into the contingency part of our understanding of evolution and the real nature of evolution, which is maybe one of the major contributions that macro paleontologists as Mike and myself can say about evolution. So we can add to all the deterministic and the fantastic laws that evolutionary biologists can test in their laboratories. We can add this importance of these contingent events that are really the marker, the shifts of history of life, and that have this both interesting dynamic in what is happening in between organisms, and so what is happening to the classical relationships between predator and prey, between parasites and hosts during this major shift, and all the phenomena that have that are pushing the entire system from outside to these new stages. So I'm thinking, for example, to major anoxic event, major events of global warming, major events of ocean acidification. So these major triggers that are not and they cannot be understood as while studying the relationships between single organisms or single groups of organisms, but you need to add this other level, that is the level of the macroevolution, that paleontologists can see directly from the rocks, and they therefore can provide in a way that it's that cannot be studied by biologists in their laboratories.
So continuing on this path of contingency and of macroevolution, Professor Benton, during these great perturbations in the history of life, mass extinctions, do the great evolutionary laws, such natural selection, still function, or are they completely suspended?
Yes, this is a very important question because, and paleontologists have discussed this, and biologists, it's almost philosophical, what is a law in biology? And I think mostly we agree they're not like laws in physics, but nonetheless, there are some principles or things which can be predicted. But of course, mass extinctions probably cannot. And as Massimo says, you couldn't predict them simply by studying genetics of living organisms, for example. And David Raab, who was one of the first paleontologists to discuss this question, he compared mass extinctions to a so-called field of bullets. So he was thinking of the wars of the past, the First World War, where he was imagining you have 100 soldiers getting ready to fight. And maybe half of those soldiers would be very strong and well-fed and well-trained. And the other half would be weak and wouldn't know how to use their gun, would be in terrible condition. But when the whistle blows, they climb out of the trench, they run it towards the enemy, and the field of bullets just kills them all. Nothing to do with normal natural selection. The strong soldiers should succeed. The weak soldiers should fail. But of course, that doesn't happen during a mass extinction event because the driver of the crisis is not predictable in terms of normal evolutionary challenges. So natural selection works in normal circumstances where a species is adapted to the particular range of temperature, climate, other features of the landscape. It's adapted to times when food is scarce and times when there is plenty of food, and reproduction is timed to the correct point where there is plenty of food when the babies emerge, etc., etc. But of course, when the extinction happens, it may be driven by, of course, impact of a meteorite, but whatever the cause, the stress will be unusual temperature or unusual acid rain or unusual other conditions. And nothing can cope because there is nothing in the previous genetic history of that species. And so I think Raup was correct that mostly mostly species cannot be adapted to the crisis that happens. And so you could not predict probably in advance. People have constantly looked at this question. We call it selectivity. Can you predict that why did dinosaurs die out? Why did ammonites die out, but mammals survived? And we could say, oh, the mammals were small, or they were warm-blooded. Maybe they were just lucky. Or maybe there is a little bit of something about being warm-blooded, something about being intelligent, or something that enabled the mammals to survive a little bit better than the dinosaurs, but it mainly seems to be bad luck.
Professor Bernardi, let's take one case, one out of the big five, the greatest mass extinctions. I think the most severe was the Permian extinction, happened 250 million years ago. What do we know now of that tragedy, and how did life manage to recover after that disaster?
Well, we know increasingly more, and this is the most fascinating part, I would say, for one that who doesn't know anything about mass extinction, that if you take the books that have been, or papers that have been written on this subject in the last decades, you constantly see that things are changing. We know more and more, and the rocks are the same. They have been there for hundreds of years and have been studied increasingly in these years, but mostly we have new techniques that enables us to read better those rocks. For example, I'm thinking about the dating of the rocks. In the study of mass extinction is obviously crucial, because when you are comparing events that are happening in different parts of the world, and you are looking at what is happening, let's say stage by stage, minute by minute, the more precisely you date the rocks, and better you can get the picture of what is happening. And studying mass extinction, it's a very interesting, I would say, approach to paleontology, because you cannot rely on photographs of the past. So drawing scenarios of what is happening in a specific time during the past, but you have to look at a short movie, at least at a short video, because you have to understand what is happening through the event. So you have to have a very clear idea of, for example, ecosystem composition before the event, during the event, and after the event. Only if you have at least, let's say, these 3 moments in time, you can really describe what is happening through a mass extinction. And for the Permo-Triassic mass extinction, fortunately, there are a number of places in the world where you can study the different environments of the late Permian through the early Triassic. For example, in Italy, we have quite a good record of late Triassic terrestrial ecosystems and late Permian terrestrial ecosystem and early Triassic marine ecosystems. So if you take these 2 bits and you add those to all the others that are in the world, you can really depict what was happening through these few million years of catastrophic event. For this mass extinction, we are now sure that it was triggered by a major volcanic eruption. It's one of those so-called lips, so large igneous provinces that was activated in an area that now sits in Siberia. Other theories, as for example, the meteorite impact that was put forward also for this mass extinction, are not well supported, and therefore we think that this is the major trigger. But as Doug Ervin said once, and I think it's a very good and very clear depiction of what is happening during a mass extinction event, he said that during the Permian Triassic event, it happened something like during the murder on the Orient Express movie. So there is a certain point that you are not really able to understand who is the killer, who is triggering that event, because there are so many possible triggers, so many possible killing mechanisms, that is really hard to understand what was happening. And in fact, also Mike Benton published a few years ago a fantastic network in which you see all the possible connections of the killing mechanism, that starting from the major volcanic eruptions and therefore the obvious physical, atmospherical products that have been that were altered by that major events. Then they all connected in a very peculiar way that was so strong to kill something like 90–95% of life that was living at the time. And it has really to be a very how to say complex and are incredibly unlucky series of connections between those events that put life into crisis. Because although mass extinctions are probably not 5, as we were saying, but maybe, I don't know, for example, in a paper by Bond and Gatsby a few years ago, they calculated 17 events. Okay, let's say they are from 5 to 20. Anyway, this says that through the hundreds of millions of years of life, there are relatively few the moments, the times in which life goes so close to total extinction. So that means that life is actually really resilient. It's really strong, able to buffer all these perturbations that normally happen during the history of life. But in this specific moment, something in this cascade of events that is triggered by, for example, a major volcanic eruption that happened at the end of the Permian, but also for other so-called mass extinctions. So then it's this very complex interlink between those triggers that at the end brought to a mass extinction scenario. And during the late Permian, most probably this is what happened. The volcanic eruptions triggered anoxia, global warming, ocean acidification, atmospheric chemistry totally altered, therefore acid rains and so on the lands, and then also in the oceans. And this happened, and this is maybe interesting for us talking more broadly about mass extinctions. Also, possibly, and this maybe Mike will elaborate on this, also possibly because just few million years before, another mass extinctions, although not so deep, not so profound, happened on especially terrestrial ecosystems. And this is very interesting because it brought us to a new scenario on mass extinction, in which these are not alone, let's say, in their role, in their role in pushing ecosystems through dismantling and catastrophe, but maybe there is a kind of connection between the health of the ecosystems before this event and how they react then to the new perturbation. And also possibly on recovery times, that it's another huge area of debate. So how long and how do ecosystem restructure, rebuild after this event? So how it is the aftermath of the events. Also for this major mass extinction, Permo-Triassic, we changed quite a lot our scenario. So we still think that it took millions and millions of years to recover the complexity of the ecosystems as before the event. But we are understanding thanks also to this more precise dating that I was mentioning few minutes ago, that understanding that some groups recovered much earlier than others, that in some areas of the world, some ecosystems were probably, how to say, less affected by the global change. And also we are understanding that some places of the world that seem to be completely vacated of life during these events, with the data that we have just a few years ago, we are now understanding that life was actually there, but was obviously struggling. It was obviously very tough to survive this event. For example, with Mike, we did a study a few years ago on tetrapods and discovered that during the Permo-Triassic mass extinction, they migrated polarward. So all those that were in the equatorial and tropical belts, in general, let's say, the general trend, it's a polarward migration. So they tried to escape the extremely hot equatorial region and moved toward the temperate areas. But also we discovered that some groups still were present at the equatorial belt, where our understanding now it's of maybe 40 or 42 degrees in the oceans during that time. So it was probably extremely hot, boiling hot. But nevertheless, some groups were able to cope with these extreme environments and stay there. So life continued also in these incredibly stressing environments. For example, those that were already, and this is a key word, so they were, let's say, pre-adapted, they were already adapted to particular environments, for example, the fossorial tetrapods. So those who lived inside the soil, inside under the surface of the ground. And so this was a strategy that was obviously not evolved during the event, but was there and was available for some groups, and it allowed some to cope and to stay in those places, even if they became nearly impossible, nearly, let's say, extreme, let's say, for most of the groups. But maybe Mike can elaborate on this.
Yeah, so the end Permian mass extinction has been a great one to study, because I think everybody gets excited about the end Cretaceous because it was the end of the dinosaurs, but it was the impact of an asteroid. And I remember back in the 1980s when I started to be interested in this, that people thought maybe now we've got a general model that all of these big extinctions were caused by impacts. And there was a big effort then to link the two. And that was quite exciting, because clearly if that were the case, this would be a really big, astonishing discovery that from time to time, every 20 or 30 million years, the Earth was hit by asteroids, but then there'd be nothing to learn from it, or at least you could predict when the next one is coming. But that's now been completely thrown aside. And I think, as Massimo was saying, much more importantly, we realized that many of the events had fundamentally a volcanic cause, and they're entirely earthbound. And the killers are phenomena that concern us today: excess greenhouse gases and acidification. These are the two big concerns we have at the moment. And we think of warming, we know that, and we observe it, and temperatures have gone up by 1 or 1.5 degrees, and we see this everywhere over the Earth. And whereas in Europe and North America, people may joke about it and say, oh, this is nice, we get a longer summer. If you live in Africa around the Sahara Desert, this is not good, because every year, thousands of square kilometers of land are becoming unoccupied. Impossible, and creating terrible crisis, not only for people, but for wildlife. Secondly, acidification is a result of also the same greenhouse gases mixing with water and producing acid. And some of the other gases that come out of volcanoes, including sulfates, produce sulfuric acid, like battery acid. That falls out of the sky, that kills the trees, it goes into the seawater. Even a small acidification of the ocean will cause the shells, the material of the skeleton of mollusks and of corals to dissolve. bad news. And of course, we are producing both of these phenomena, warming and acidification, by human activity. And the generality of that, as Massimo commented, is that not only the end Permian event, but it seems there were another 5 or 6 crises through the Permian and Triassic that were all caused by the same process. Different volcanic eruptions each time. So it might be a volcano in Russia, as at the end of the Permian. It might be volcanoes in China or in the North Atlantic, or even in Canada. And each of these corresponds to one of these crises. But we do understand a little bit about when volcanoes erupt, not a great deal. There are volcanic observatories in Italy, which have many highly skilled volcanologists, and they're often thought to be not competent because they don't predict volcanic eruptions. They do their best. It is difficult, even if you're sitting there. But nonetheless, it's within the earth, and it's something that we can try to understand. And then secondly, the consequences we can observe, because with any volcanic eruption, we can see exactly what happens. Luckily, most of the eruptions in our lifetime are very small, and they just have a local effect. But there can be huge eruptions that then have a global effect. And so that has now become a whole new way of understanding some kind of general principles of Earth crisis. And I suppose the final thing is, having commented on acid rain, which obviously will massively kill most marine organisms, and we mustn't forget the microscopic plankton, because a lot of them have shells of calcium carbonate as well. Secondly, the warming, as Massimo commented, we have very good evidence that after the Permian event, ocean temperatures rose substantially. 42 degrees is a very hot shower. And you might think that's okay, but you wouldn't want to stand in that very hot shower or that sauna for day after day after day. It would kill you. And no living thing, no plant or animal is happy at 40 degrees. The best adapted desert living animals can cope at maybe 35 degrees, and tropical organisms. So if you raise the temperature from 35 to 40, it's only 5 degrees, you clear the tropics. And we're seeing that happening today, and this is what happened in the past. That puts on pressure. Couple that with acid rain, which on land kills the forests, removes the basis of the food chain, of course, stops the oxygen going into the atmosphere that the forests would be producing, removes the food, the herbivores die, the carnivores die. And so, and geologically speaking, these processes are fast. Even ecologically speaking, these processes would be happening within, at most, 2 or 3 years. And geologically, that's very, very fast.
So my last question for you, Professor Benton, you partially answered to that, but drawing from all that we said and from all that you paleontologists studied and learned from the study of the mass extinctions, what can we learn and what can we apply of this knowledge to today? In the present, we are on the brink of the 6th mass extinction, and the difference is that one species, caused that. We are like a big volcano for the Earth.
I think I'd like to say first that we're more confident now about what we think we know than we were in the past. And that's a point that Massimo made earlier, but I think this is very important as part of a statement, if you like, about the importance of understanding the past. So when I started studying mass extinctions a number of years ago, our knowledge of the dating was very poor, and Massimo has pointed that out, that now this has improved a great deal. And in the case of the end Permian event, although it is 252 million years ago, we can discriminate time spans of maybe 60,000 years. So different phases of the event may be separated by just 60,000 years. And that is a kind of precision that people would not have believed 10, 20 years ago. Secondly, we can determine paleotemperatures with considerable confidence, because these can be measured from oxygen isotopes within the shells of organisms, even within the sediments. And they are measured in many, many sections around the world. So Massimo talked about the wonderful sections in North Italy, and there are similar sections in China, Canada, Russia, many parts of the world. And so people have measured the oxygen isotopes, and you end up with these wiggly lines, these zigzag lines going through time, and you check this place, this place, this place, this place. And so now across that particular boundary, there must be more than 100 really precise, accurate sections have been measured where we can detect +2 degrees, -3 degrees, +5 degrees, -2 degrees. And so those methods are really good. They're being tested and tested again. The laboratory equipment and the ability to measure is better than it ever was, and quick and automated. And people are very concerned to get it right, because of course, a point about this area of science, like all the others are, if you get it wrong, or if you overstate something, another scientist will very helpfully tell you, and with great pleasure, they will come along and say, you got it wrong. So I do want to say that if people think we're delving deep into the past and that therefore it's all just guesswork, if you do not have a time machine, how on earth can you know these things? I would like to just put those 2 points, that in fact, we're very, very, very concerned that we get these things right. And we say we know these things because we have evidence. We don't say them because I am a professor, you should believe what I say. So yes, and then knowing those things, what it means is we have access to a number of experiments that have already been run. If you were a futurologist, a person who tries to use current knowledge to predict the future, you could propose to the United Nations, let us do a great experiment. We would like to discover the effect of raising global temperatures by 10 degrees. We can do that if we release nuclear energy in a massive way, and we monitor this, and of course, it will kill many people, it will kill many animals and plants, but this is an experiment that we could do. I don't think you would get permission to do that. But we don't have to do it because it has been done in the past. This is the key point. And so another part of science that is a problem for us is repeatability. We can't repeat an experiment like you can in the laboratory, like you can when you're testing vaccines for the virus. You can test, does it work, does it not work? But we have these, and therefore, because there seems to be a kind of common model, we have then 5 or 6 events definitely that are well studied that we can look at, and we would say there is a repeatability now. This is something that's become clear in the last 10 years, that then says, if you raise the temperature this amount, this is what might happen. If you impose a certain amount of acidification of the atmosphere, these are the kinds of things that will happen. And so I think there's a great deal of predictability, and then you couple that with, my final point will be, and then Massimo can go and tell us exactly what's going to happen in the next 100 years. I'm just setting him up. The final point is that together with the improvements in laboratory, mainly chemistry precision that we can use in these cases, improvements in the chemistry, has come a great improvement in methods of computation. So computers are bigger, we can run analyses with all kinds of uncertainty. So you're not putting in a single value, you're putting in all kinds of uncertainty, bias, difficulty, and you can run the analysis with many repeats and many tests. And of course, now we have climate models, which all of the meteorology agencies in the world use to give the daily weather forecast. But those kinds of models are used, of course, to look at the present day. What's the effect of this hurricane? We can model the hurricane as it comes across the Atlantic, and we'll say, okay, in a month's time, this will happen. But those models now are applied in the past. So we have Triassic climate models, which are based upon these modern ones, and they're getting more and more detailed all the time. The computing power is huge, but it actually allows you then to feed data, which I would argue is now held quite confidently, feed the data into the model, run the model using computing power that we could only dream of 10 years ago. and get some kind of result with a measure of confidence as well. And so I think all of that provides some strength to our ability to predict into the future.
So Professor Bernardi, what will happen in the next 100 years?
Thanks, Mike.
You're welcome.
Obviously, I won't be able to answer this question, but I can only add something. This is what we know, and this is how we can use this knowledge. And there is an entire new discipline that is called conservation paleobiology that tries to use some of this data from the past and integrate those to the models we are building today to try to understand what will happen in the future. So this is actually working, and I think this is a great step for paleontology that can be helpful also for understanding of the present and future dynamics. And there is also maybe another thing that we can add that stems from what we have understood, that is maybe more philosophical, but I guess really relevant for our for tackling this crisis in which we are in. That has more to do with the fact that Georges Cuvier, which was one of the first to think and understand the dynamics of mass extinction, used to call this event revolutions. And I think this is a very good word to describe these events. We are used to think about extinction literally, so everything dies. But these are not mass extinction. Life is still here after a number of mass extinctions. That means that life constantly finds the way, or it is lucky enough to have a way to go out from this event. But life after this event is never like the one that was before, and therefore here we are. So we are exactly in this peculiar perturbation in which we are obviously trying to find a way to go on the other side. But we know that life will be on the other side. So this is not the end of the world. No? You know, catastrophic movements and in general nihilistic approaches are spreading. But we know that this is not the end of life. It's just one of the events of deep perturbation. So things will deeply change. We'll drastically change. But life will be on the other side, and the way in which we will live in that other world, IUCN predicts that the risk of extinction of Homo sapiens is really very small. We are a lot of people, we are everywhere in the world, we have technology, so it is very improbable that our species will get extinct during this sixth mass extinction, or however we want to call it. The real question is what the world will look like after this transition, or during this very dramatic transition that we are living in. And so maybe this is a more interesting question. We are used to try to find always the finish, the ending point, but we are in the middle, and maybe it doesn't really make much sense to think about the end of the story. We are in this chapter of the story. Things are changing very rapidly. World around us is changing, and how we will deal with these rapid perturbations that will happen nevertheless. It's maybe a more interesting question for scientists, and also maybe for philosophers and for sociologists. So all those who try to tackle and maybe create a model of what will happen in the future. So paleontology is very clear on this. Life goes on differently, but life goes on.
I think I'll just briefly add, if I may, that's absolutely right. And I think we can see things happening, and they tie with what we would predict. And of course, as temperatures go up, even just by 1 degree, we see melting of the polar ice caps. It's happening, it's documented every day. And I think the predictions there can be quite precise now. We know exactly what's happening. You can see it, and you don't need geology or paleontology there. And I think the movement of climate zones is very clear. It's even happened long before the current crisis. We recall that North Africa was seen as the source of wheat and grain for the Roman Empire. That now seems unbelievable, and would have been unbelievable even 500 years ago, because climate had already changed. And I think this is part of the problem in politics, that the people are not well educated in science, and they sort of think, oh, well, if climate changes, this is all right. But there's a very definite link. And I think that although we see species moving, of course, the other big threat we've not talked about, which is not predictable from geology, is competition for space between Homo sapiens and the rest of nature. So Homo sapiens is the most successful species ever, probably, in terms of dominating the Earth. But in dominating the Earth, we're killing species. And there are many, many species of plants and animals that don't exist worldwide. They're only known from small areas. We do have nature reserves and other ways of trying to hold on. And I think it's commonplace as well for the public to understand that big animals like whales and elephants need big spaces. And we are not providing those big spaces. And it's not enough just to give them a little piece of land here or a little piece there. And even the Galapagos Islands, where Darwin made so many studies, are occupied by people who are trying to survive and living a poor existence. But whatever you do, in a way, we are intruding, we're causing problems. And so, but as Massimo says, yes, in the end, doubtless we will survive together with the cockroaches and the rats and all the other very successful species on the Earth. But a lot of very colorful species like rhinoceroses and elephants and many tropical birds and plants will sadly disappear.